Fructose is another common monosaccharide, and like glucose, it has 6 carbons. But unlike glucose, it is a ketose. It has a ketone functionality. And according to the Fisher projection, only 3 chirocarbons as opposed to 4. Fructose, like glucose, will form a ring structure in solution, and unlike glucose, it forms a 5-membered ring. So a 5-membered ring that has 4 carbon atoms and 1 oxygen atom is known as a furanose. Like glucose, the anomeric carbon in fructose bonds with the oxygen from the hydroxyl group on the carbon 5. So we see this sort of the same mechanism of forming this ring structure where this oxygen in the hydroxyl group forms this hemiacetal bond with the anomeric carbon, and the oxygen that was originally in this carbonyl bond takes the hydrogen from the carbon 5 hydroxyl group, and then it becomes a hydroxyl group. And the hydroxyl group that is formed from on the anomeric carbon can either be below the plane for the alpha isomer or anomer, and the hydroxyl group can be above the plane of the ring for the beta anomer. So when the anomeric hydroxyl group is on the same side as C6, excuse me, that's beta, and when the anomeric hydroxyl group is on opposite sides of the C6, that's known as alpha. Now, the anomeric carbon also is bonded to C1. So in glucose, the anomeric carbon is bonded to hydrogen, but in fructose, it's bonded to C1, so CH2OH. And like glucose, when we figure out what the carbons will have attached to them, the arrangement in the ring, we look to the Fisher projection. So carbon 2 is our anomeric carbon. Carbon 1 is going to be attached to our anomeric carbon, and if we know whether the anomer is alpha or beta, we'll know where carbon 1 will be, either above or below the plane. Carbon 3 in our Fisher projection has hydroxyl on the left, so that means carbon 3 will have hydroxyl above the plane. Carbon 4 has hydrogen to the left, so that means carbon 4 will have hydrogen above the plane. And then carbon 5 always has carbon 6 above the plane.